Hello guys, in this video we are going to talk about the stress-strain diagram of materials. As you can see, the vertical axis of this diagram is a stress and the horizontal axis is a strain. And this curve is plotted as a result of the tensile test. It has two different zones, elastic zone and the plastic zone, that we will discuss it right here. So at first we should know the type of deformation of the material. At first, the elastic deformation, which is happen in the elastic zone. The elastic deformation return to its initial size or shape after the removal of the force. It means if you're pulling a specimen of material right away after you stop the loading of the force, the material can return to its original or its initial shape and size. So we call this type of deformation reversible deformation. Elastic deformation is reversible. On the opposite side, we have plastic deformation. In plastic deformation, material does not return to its initial size and shape after the loading of the force is removed, and the deformation is permanent. So plastic deformation is irreversible, which means that you cannot go back to initial size and shape after the removal of the stress.
Initial size and shape after the removal of the stress. So now let's talk about the elastic zone and the plastic zone in the curves. As you see in here, in elastic zone, the curve is linear and the hooks law is oblique in this zone of the diagram, which say a stress is equal to Young modulus multiplied by a strength. We can see it essentially we can see the hooks law here in the elastic zone of the curves. As we can see, the Young modulus is the slope of the diagram of the linear curve. Here, so this the Hooke's law, and we have here the stress in the elastic zone, which is the maximum amount of stress that a material can take right before the plastic deformation. So this is the yield stress of the material. We saw it with sigma, and after the elastic zoom we can see in the plastic area. In the plastic zoom, the curves is not linear anymore, so the Hooke's law is not oblique. Here we have two different parts, strength hardening and the necking part.
In the strain hardening part of the plastic zone, we can see that the slope of the diagram is positive. It means that we need more stress for deformation. We need more stress to have certain amount of strain. So the reason is that the straightening with dislocation pile up and blockage happens here. It means that when you enter the plastic deformation zone, when the plastic deformation starts, we have the generation of a lot of dislocations. A high number of dislocations are generated, and they can pile up and blockage each other's way, and this can cause strengthening in the material, which means that we need more stress to cause certain amount of strain. And the equation of this part of the diagram, strain hardening part of the plastic zone, is here. Sigma stress is equal to K multiplied by E to the power of N. The sigma is stress and epsilon is a strain. We know it. K is a coefficient and N has a number. between 0.1 to 0.5 or 0.6. So this equation is obeyed in the strain hardening zone of the material.
And in the highest amount, in the highest part of the curve in the plastic zone, we have ultimate tensile strength, which is right here. It is the highest amount. It is the highest amount of stress that a material can take or endure, and it is very important. Quantity is in material properties of material is the abbreviation of ultimate tensile the strength. So we had a Euler strength in here and tensile strength in here. These two important quantity in the necking on the opposite side of the strength hardening zone. We have the slope of the diagram is negative, which means that we can deform the material with less stress, or the certain amount of stressing can be achieved with less stress. As you can see, the curve is decreasing, which means we need less stress for deformation. And if we want to know the ratio, we can say that the large amounts of a string is localized disproportion in a small region, so the ratio is the localization of strength in the small area of the cross-sectional area of the material,
which is called the decrease in cross-sectional area. And when the decreasing cross-sectional area happens, it means that we need less stress to deform the material because the area is decreased, the area is smaller, so that we need is smaller so we can deform it with less stress. And this is a very bad part for the mechanical properties of the material. When this happens, that we understand that the material or the specimen is near the fracture, because after the necking, the fracture of the material happens, where the material this or specimen breaks and the test is over in here and the curve is over too. You have another concept that is related to this stress strength curve, which is toughness. Toughness, do not mistake it with the strength. In a strength, the strength is the ability of the material to resist the stress that resists the plastic or elastic deformation. So it is the ability of material to resist against the deformation of the material. But the toughness is the ability of the material to absorb energy in the form of deformation before fracture. So the toughness is the ability of material to absorb energy in the unit of volume.
So, the toughness is the ability of material to absorb energy in the unit of volume, and the R of the toughness is usually measured from the integral from 0 to AF, which is the strength factor right here. For example, trace a string, so we can calculate the toughness of the material or the absorbed energy of the material right before the fracture. From this integral, you can see this is the area under the diagram are under the curve. So if we have the area under the curve, we can have or understand the toughness or the absorbed energy of the material before fracture. So we can say the area under the curve is higher, then the toughness of the material is higher too, and if it is lower, the area under the curve is lower, it's a smaller area, the toughness of the material is lower. Thank you for your attention. Goodbye.